The goal of this video is to provide a basic introduction to the idea of what is finite element analysis, or FEA. Welcome to an introduction to finite element analysis. As you can see, this video is going to consist of a bunch of boring PowerPoint slides, going one right after the other. Here's a quick example of a simulation you can run in FEA. Car running into a wall. Very complex situation, lots of things going on. The loading on individual components is very complex, and yet with an appropriately sized FEA model, you can simulate with a high degree of accuracy what goes on in this event. Let's start off today's topic by taking a little quiz. What exactly is finite element analysis? Is it a graphics tool that can be used to make pretty pictures? Is it a perfect example of if you put garbage into a system, you will get garbage out? Is it a powerful stress analysis tool? Or is it a mathematical tool for solving boundary value problems? Or E, is it all of the above? So let's talk about what FEA is then. What is the big picture of what goes on? So we'll start out with a complicated problem. For example, here's the Cal Poly Rose float frame. Take this problem and break it into a bunch of smaller pieces. We can manage things in smaller pieces. We can figure out what's going on in a smaller piece. We're going to call each of those pieces an element, and we're going to limit ourselves to a non-infinite problem. So it's a finite number of elements. There might be hundreds, there might be thousands, there might be millions, but it's a finite number. Then we're going to look at each piece and come up with a very simple description of what's going on in that piece. Oftentimes a linear relationship between stress and strain, or between force and displacement. Then we're going to take all of those pieces and show that they have to relate to each other using compatibility or continuity equations. We're going to link them together, and this will give us a large system of equations. We're going to assemble them into matrix form and get an equation like what's shown here, F equals KD. Then we're going to solve that matrix equation. So the basic idea of FEA is you have an equation where all of the forces equals all of the stiffnesses multiplied by all of the displacements, and you typically know the stiffnesses because that's your structure, and most of the forces, but you don't know the displacements. So in order to solve the problem, we have to find the inverse of the stiffness matrix K, and that will then give us all of the displacements. So that's the big picture in FEA. So what kind of problems can FEA solve? Well, FEA can solve any kind of boundary value problem, or BVP. A boundary value problem is a mathematical problem in which the quantity of interest is defined by a differential equation that covers it throughout a region. The quantity of interest is only actually known in specific areas called the region's boundaries, and we need to use either the differential equation to determine the value of the quantity of interest internally, or some other method. Some common BVPs in engineering include stress analysis, where we are looking for displacements and stresses internally, but we know displacements and loads externally. Heat transfer, where we know temperature and heat flux on the surface, but we don't know what's going on internally. Or fluid flow, or electrical or magnetic potential. All of these can also be considered to be a static or steady state problem, or a time-dependent or dynamic sort of problem. Let's dive into the finite element process from the user perspective. What do you as the user experience when you are running FEA? So first off, as the user, you need to figure out what you know and what you don't know. This is how you solve any problem. So it's no different with FEA. Define the problem up front. Then create a clean model. So specify the geometry, the material properties, simplify the geometry, and we'll talk more about this, and we'll see examples of unsimplified geometry causing problems in FEA. So simplify it, provide material properties. Then define how the model is restrained from motion, or restrained from heat transfer conditions, or whatever the type of analysis you're doing. Apply the loads to it. In the case of a mechanical system, that's a physical force, but loads might be heat fluxes in the case of a heat transfer analysis. Then break up the model into pieces. As I said, with the big picture, you want to look at a finite number of elements inside. So here's an example of a finite element mesh on the simple model we started with. Then define how you're going to analyze it. what is the relevant physics behind the problem. You submit the job to the computer to go solve it using the black box. Now the black box will no longer be a black box after this class, but for an FE analyst, if you trust your code, then it's sending it to the black box to solve it. And then you get the results back, the deformed shape, the stresses, the energy content in strain, all kinds of information comes back. And then you need to determine if it is reasonable. You need to go through a post-processing operation. That's an overview of the user perspective. Okay, so now let's talk about what happens once the user submits a job. What is the black box doing? So first off, the computer will identify the element stiffness relationship inside every single element that you have defined. The simple relationship is you've got some forces acting at points on the elements. They are related to the displacements of those same points by stiffness of the element. So F equals KD is the basic equation. You have one of those for every element. So you have 10,000 elements, you have 10,000 matrix equations initially. Then you apply some conditions, we call them continuity equations, that specify that the material doesn't rip or doesn't overlap on itself. These are physical conditions provided you don't have structural failure. And if we apply them, it allows us to link all of the equations that are in all of the elements. When you link them together, you end up with a single matrix equation, F equals KD. Notice it's all caps now. Then you apply some boundary conditions. So you specify what points are actually known displacements. And when you do that, for computational reasons, we actually modify the stiffness matrix and the displacement vector and the force vector. So putting the BC for boundary conditions in each of them. We'll talk about this later on in the video series. Then finally, you take the inverse of the KBC matrix, and that allows you to come up with a vector of now known displacements. So DBC would be all the known displacements. And then finally, you do the post-processing. So you go back to each element, you interpolate local displacements and stresses in them. Let's go over some basic FEA terminology. We have here a finite element analysis model, and we can identify an element as being a single piece of the structure shown here. Another key term is a node. A node is a point where elements attach or meet each other, or on the boundary of an element. Another important term is a boundary condition or a constraint. This is where we specify a known value of a displacement. And then we've got nodal loads. These are forces or other types of loads that are applied to a node. There are some other terms that are going to be important to know. Start out with the degree of freedom. A degree of freedom is, in the case of stress analysis, simply the displacement of a node. And it's the displacement that is specifically resisted by the elements that the node is attached to. But more generally, you can think of a degree of freedom as some property of a node, like the temperature or the electrical charge, that relates to the attached element stiffness matrix, whatever it is. The next important term would be a nodal displacement vector. This is also known as the degree of freedom vector, and it's what I had as a little d or big D in the earlier slides. This is the vector of all of the degrees of freedoms at that node in the element or the model. So that would be displacement in the x, y, and z direction for a 3D model, or perhaps rotations about certain axes, or perhaps it's temperatures for a thermal analysis. Next, the nodal load vector. This corresponds to the displacement vector, and it's the vector of all of the components of the loads at all of the nodes. So if we look at a displacement vector and we have translation in x, y, and z at nodes 1, 2, and 3, then we would have a load vector that corresponds to that, which would be the force in direction x, y, and z, and this corresponding to nodes 1, 2, and 3. A stiffness matrix is what relates the displacement vector to the nodal load vector. So the stiffness matrix is always a square matrix, and it has the number of columns and rows corresponding to the total number of degrees of freedom in the element or in the entire model. So the lowercase, by the way, throughout here I'm using to indicate the element properties, and the uppercase correspond to the whole system properties after we assemble them. A singular matrix is another important concept that we need to have in FEA. This is a matrix that simply cannot be inverted. You can evaluate it by determining the determinant of the matrix, and if the determinant is 0, then the matrix cannot be inverted. But it means something even more important in FEA. It means that there is no unique solution to the system of equations that the matrix represents. That is typically caused by a problem in which you haven't fully tied things down. So if you apply a force to a system and you expect it to be static, but there are improper constraints on the system, then the system will move, or in FEA terms, you will have a singular matrix and you cannot solve the problem. So back to this quiz that I gave you at the beginning. What is FEA? Is it a graphics tool used to make pretty pictures for business meetings? Is it a perfect example of put garbage into a system, you will get garbage back out? Or is it a powerful stress analysis tool? Or a method for solving boundary value problems? Or is it all of the above? It is, of course, all of the above in many situations. Hopefully at the end of this course, you will be using it as a powerful stress analysis tool, or perhaps as a more broader method for solving boundary value problems. And you will also be able to identify those other finite element analysts out there who use it purely as a graphics tool to make those pretty pictures. You can ask the right questions, probe deep, and understand if the results are valid or if it's just a pretty picture.